friends, today I'm going to solve LeetCode problem number 109, convert sorted list to binary search tree. In this problem, we are given the head of a singly linked list and elements are sorted in this list in an ascending order. So we need to now use this linked list and convert it into a height balanced binary search tree. So what's a height balanced binary search tree? It is a binary tree in which the depth of the two subtrees differ only by 1. So let's look at this example here and see what does that mean. So all right, let's just see some examples. So this is only one node and the height of this tree, which is equals to 1, it doesn't have any subtrees, so it's still a height balanced binary search tree. When we create a node, when you add a node to its left, it's still a binary search tree which is height balanced, because the difference between its left subtree and the right subtree, which is a null, so the difference between the length is equals to 1, because this has a depth of 1 and this has a depth of 0, so difference is only 1, right? So that would be similar if we add more nodes here. So suppose we added more nodes here and then we add one more node here and there is no node, still the depth of this tree is 1 2, so that's 2, and this depth is 1, so the difference is still 1, so that is why this is still a balanced search tree, binary search tree. Now if in case we had one tree here, a root here, and one more node here, then in that case it would not be a balanced height binary search tree, because then now the height here is 3 and here it's 1 and the difference is equals to 2, which is greater than 1. For a balanced height binary search tree, it should only be 1 difference. So that's why we know that this is not a balanced binary search tree. So now how could we make a tree balanced? Let's just take few examples here. These are sorted numbers, so we are going to create a binary search tree using these numbers. So we are given these numbers. So for a tree to be balanced, well, suppose you are here. Now for the tree to be balanced, okay, let me just create a node here. For the tree to be balanced, there should be either equal number of nodes on both the side, or if it only differs by one node. So if it is here and then this, if this is then -1, that is when we could create a balanced height binary search tree. How is that possible? Let's look at this example here. So what we do is we take the middle value of these series of numbers. So we have 1 2 3 4 5 6 7. So what's the middle value of 7? That's 3.5. We are taking the ceiling value, so this would be 4, right? 1 2 3 1 2 3. So we have equal numbers towards the left to the right. So 4 is our root node. Now how could we create this this tree? Is now we go towards this left. So when we look at this whole thing here, we need to create a tree, a subtree for this one. So basically we are splitting this whole big problem into smaller problems. So now we take a look at this series of numbers 1 2 and 3, and then we found the middle value here, which is equals to 2. So we construct 2 as the root node here, and then now this goes to the left and this should be goes to the right subtree. So how do we know that which value should go to left, which value should go to the right? Because we are dividing it from the middle. So now this goes to the left and the middle value of this itself is the node itself, the value itself. So we create a node with a value 1, and again for this one we do the same thing, we create a node with a value 3. And now what we do is, since this is towards the left, we join this with a branch. So this becomes the left subtree, this becomes the right subtree, and we see it's balanced, right? And now we do the same thing here. Since this is this whole portion is towards the left, we add this subtree towards the left branch of this node. So now this whole thing will go towards the right. So the node that is connected to 4 would be the middle value, that is equals to 6. So we connect the value node 6 with the node 4, and then now node 5, this whole thing will go towards the left of root node 6. So since this is the only value remaining, this will go to the left, and then towards its right we will add this value 7. So what did we create? We actually created a balanced height subtree, because the height of both of its subtree are equal, right? So that is how we create a balanced height subtree. So this is what we are going to do for this example here as well. So we take 0 as its root node. Now we have -10 and -3 towards its left. So what would be the node that will connect to the left? What will be the child node, left child node? So that is what we take the middle value, and we are taking the ceiling value. So between these two, the middle value would be the -3, which is the ceiling value as well. So we add -3 as its left child, and then now this whole thing goes towards the left of -3, and since it is the only root node, so we add -10 to this tree. Now next what we do is towards the right, we have these two nodes, right, and we take the ceiling value, and what we find is 9 would be the node that is connected to node 0, right, because we are taking the ceiling value. So 9, we add the value 9 as its right node, and then now for value 5, since it is towards the left of this root, towards left of the value 9, we add it towards the left branch. So we add the value 5 towards its left, and that is what we get. So this is what our final answer would look like. So basically what we are doing is we are dividing each problem into sub problems, and we divide it using the middle value, and we are adding the branches to the left and to the right based on based on where we divide it. So now that we know how we could solve this problem, let's actually code this problem. So let's first of all look at the edge case. So what would the edge case be? The number of nodes in the head can be in the range 0 to 2 to power 10, 2 times 10 to power 4. So well, the head could be an empty node, that is null nodes, that is there may not be any node. So if that's the case, what are we able to create a tree using a null linked list? Well, of course not, right? So that is what we need to consider while we are checking for edge cases. So if we do not have any head, then we are going to return null, because we cannot create a tree. If then is there any other edge cases where there are not? So the value of now node ranges from -10 to power 5 to 10 to power 5. All right, so that's the case. So now let's start constructing our tree. So we are dividing the problem into sub problems. So what we could do is we could perform a recursive call. So let's create a recursive function, and here we are going to use dfs, depth first search recursive function, and we are going to pass left and right values. All right, so one more thing we need to keep in mind is we are given a singly linked list, and in a linked list, can we access the node using the index? Well, not, we cannot do that, right? We can either go start from the head and then continue from that until we reach that point, right? But what are we going to do here is, instead of doing that every single time, we are actually going to create a array out of the linked list, and then in array we could access each index, each value in a given index in O of 1 time complexity, right? So that is what we are going to do. It would occupy an extra space, but we are going to do it because that would be time efficient. So let us define an array and then create the array. Okay, we are going to use okay. So now we have created our array. Let's now focus on our DFS function. So how long are we going to keep continuing our DFS? As long as the value towards of left index is less than right index, right? Less than or equals to. So if the value of left index is greater than right index, we are going to return null. Else what are we going to do is we find our mid value, so that would be equals to math.ceiling value. We are using the ceiling value, left right, okay, left plus right divide by 2, and then this mid value will be our node. So now our node is equals to a new tree node with the value array m. And now we need the left and right index, right? So what are going to be our left and right indices? So left would be everything that's towards the left. So now in this example, 0 is our mid, so we constructed a node out of 0, and now we want to find its left subtree, right? So for that we need to find the node that will be attached to 0, and for that we are actually dividing this problem into the sub problem. So we pass the index starting from left to mid minus 1 in our DFS function. So left comma mid minus 1, and similarly for the right, everything towards its right will go right. So mid plus 1 comma right, and the value returned from this would be the root of this subtree. So we are going to actually return the root of this subtree to this, and that will be attached to the left. And similarly from the right, we are going to return the root of this subtree, and that will be the right of the node. So we return, every time we return the node. And finally we are going to call our DFS function and return the value returned from our DFS function. Okay, so now let's run our code and look if we find any errors. Awesome, we passed all the test cases. Let's try to submit it. Great. So now the time complexity and space complexity. For space complexity we are using an array, so that will be O of n. And for time complexity we have a while loop, this is O of n, and we have a DFS function where we are iterating over each of the node, right? So that is also O of n. So basically time complexity here is O of n.